How we doing, guys? Welcome to the channel, The Broke Diver. Today we're going to be talking about a very special topic, decompression theory, and how those principles or that science applies to recreational diving, and as well as decompression sickness. So I'm an avid recreational technical diver. Been diving all over the world, anywhere from Egypt to Mexico, Cozumel or Cenote dives in Playa, as well as a lot of technical dives in my home freshwater Lake Mead, on recreational, sites, historical sites like where the dam was built, or even these deeper wrecks where we're going down 120, 180 feet sometimes to explore these boat wrecks. What I share today is solely for information purposes, not a substitute for training from a qualified instructor or agency. However, that being said, as professionals, technical divers, or even recreational divers, I feel we need to share this information to help others make more informed, mindful decisions regarding their risk of DCS and how to reduce it. Main objectives today is going to be try to gain an understanding of decompression principles and how they apply to recreational diving. We're going to start with the physics and physiology. I apologize to those that already know this, but I need to build that foundation so we make sure we're all on the same page as we progress. From there, we're going to get into decompression sickness, the types, how that occurs, what are some of the causes and symptoms. Then we're going to move into how our dive computers protect us against decompression sickness and some of the models they use, some of the pros, cons, and how they interpret or use algorithms or math to do so. And then we're going to kind of close everything together with some of the common factors or actions we control as recreational divers that greatly affect our decompression risk or decompression sickness risk. Alright, so jump right in. Biology of gas exchange in the body. So we breathe in air into our lungs. In this case, what we call the alveoli, or little air sacs within the lungs, right? In that space, the gas we breathe in is dissolved into our blood. That blood takes that dissolved gas out into basically the tissues, whether it be your heart, your muscles, your fat, your joints, anything like that. And then on the way back, it dissolves that gas back into the blood again, where it's then taken back to the lungs, where the carbon dioxide, for example, is dissolved back into the alveoli to be breathed out. The important thing to note here is we take in all gases, so nitrogen, oxygen, for breathing a heliox mix, like a helium or even a hydrogen mix, depending on the mix we're breathing. Those all get dissolved into the blood from the gas, or from the lungs into the blood, and then the blood carries those gases out to the body tissues, where they're used or stored, and then they're taken back to the venous blood and back to the lungs. The next concept we need to understand is pressure versus depth. So as we descend in the water column, pressure around us increases. A good way to think about this is that balloon model we were probably taught in open water, right? If I take a balloon on the surface and I descend down 33 feet, it's going to be half the size. If I descend again another 33 feet, it's going to be a third of the size, and then 100 feet about a quarter of the size. This is important because as we descend, that increase in water pressure forces our lungs, just like that balloon, right, to shrink in size. However, the way we compensate for this is we breathe higher and higher PSI from the tanks or our regulators, right? So as we descend to say at 33 feet, right, pretty common depth for recreational diving, we're actually breathing 30 PSI or 29.4 PSI to inflate our lungs to the same volume, using twice the amount of pressure as on the surface. If we go a little bit deeper to 66 feet, that kind of limit for recreational diving, now we're breathing 3 times the pressure of the surface, 44 PSI from our tanks. If we go a little bit deeper, we can get up to like 58, 60 PSI as we close in on that 100-foot range. So again, as we descend in the water column, the surrounding water pressure increases, squeezing our body, squeezing our lungs. To compensate for this, we breathe higher and higher PSI to expand our lungs fully to that same volume as the surface. But to do this, we have to breathe higher and higher PSI air or gas from our tanks to do this. Well, why is that important? That's important because we're going into something called Henry's Law. So a gas's solubility, or how much gas can dissolve in a tissue or a liquid, is directly related to pressure. If we increase the pressure, we increase the amount of gas that can dissolve into solution, or the gas solubility in that solution or liquid or tissue, where it may be. Good way to think about this is a soda stream, right? So if I take this soda stream, right, put some water in it, it's open, say for example, the gas pressure on the top of the bottle is going to be equal to the gas pressure dissolved into the liquid. If I then put this bottle right into that soda stream, what happens is I inject high pressure CO2 into the bottle. That high pressure CO2 increases the pressure in this bottle up to a certain point, say 30 PSI, just as if we were diving to deeper depths, right? So breathe in higher PSI air, or gas from our tank, right? I increase the pressure this liquid sees. By increasing the pressure, more gas is going to dissolve into that liquid, in this case our blood and our tissues, right? And on ascent, right, as we come back out of the water or come out from depth, right, and ascend to the surface, the reverse is true. So all that gas that dissolved into that liquid at depth and that higher pressure wants to come back out, right? Because the pressure, as just like I open this bottle to atmosphere, you start to see that bubbling and that fizzing, right? Same thing happens. This bottle was at say 30 psi after the CO2 was injected. If I then take it off the machine, open it to atmosphere, that gas, that 30 psi of gas that's dissolved in the liquid wants to come back out of solution. It's going to form little micro bubbles and bubbles on the side and then eventually go up to the surface, right? This is what we call saturation levels. So this is very important to understand. So let's dig into this a little bit more. So on the surface, right, just as when I take this bottle right before I put it on the soda machine, we're saturated. The pressure of the gas on the surface here is equal to the pressure of the gas dissolved. We call this saturated or at equilibrium. As I increase the pressure of the gas by injecting that CO2, the higher pressure gas now, the pressure of the gas on the top, or the ambient pressure, right, is higher than the gas dissolved in the liquid. The liquid in this stage is what we would call undersaturated, right? So the gas wants to then dissolve into that liquid, just as the gas in our lungs would dissolve into our blood and then into our tissues. At some point, that becomes equal, where the pressure of the gas on above is dissolved equally into the liquid, so the pressure of the gas on the surface is equal to the pressure of the gas dissolved in the liquid. On ascent, as I take that bottle off of that soda stream, or as I ascend in the water column, right, that pressure rapidly decreases. Now, since I have less gas pressure in that space, right, or that ambient gas, the gas in my lungs, the pressure in the liquid, the pressure dissolved in the liquid wants to come out. That gas wants to come out of the liquid and go into equilibrium. So it goes from the higher pressure in the tissues, dissolves out in the form of bubbles, right, or in some cases fizzing, right, to try to get to atmosphere and lower the pressure of the gas dissolved into that liquid. A good way to think about this is the soda, right? As long as I keep the soda closed, at the factory they were going to inject that CO2 just like I do on that soda stream. They're going to increase that pressure, right, and then they're going to cap it. As long as I keep the cap on, that liquid won't have bubbles. It's going to basically stay, that gas is going to stay dissolved into that liquid. However, as soon as I open that bottle up and release that pressure on the surface or in that little vapor space, right, the gas dissolved into liquid now wants to come out of solution. It's going to form carbonation, those little micro bubbles and fizzing and foam that we like in our drink, and then it's going to eventually, as I let that bottle sit out, that gas that's dissolved in that liquid is slowly going to keep bubbling over time until all the gas that's dissolved in that liquid comes back out of that solution or releases from that solution until the pressure in the atmosphere is equal to the pressure in the liquid. This is what would happen if you put that soda on the counter, right? Eventually over time it's going to lose its carbonation to you, right? And that's because the gas is coming out of solution, out of that soda, and back to atmosphere. All right, let's jump to the next one. So what does all this mean? So gas to tissue exchange. So let's take that theory and that gas solubility and saturation type theory, and let's apply it. So as we descend on a dive, right, as we go down in the water column, we have to breathe higher and higher psi, like we talked about. Well, that higher and higher psi is now higher gas pressure than the gas that's dissolved in our tissues and in our blood, just like as we inject that CO2 in that soda stream, right? That gas then dissolves into our blood. Our blood carries that dissolved gas out to our tissues, where they absorb that. And then on ascent, as we basically start to come out of the water column, right, the reverse is true, where the gas is dissolved in our tissues. Just as we open up that soda, right, it wants to bubble and come out of our tissues, dissolve back into that venous blood, and then back to our lungs. The process as we descend, where we're taking on gas or dissolving gas into our blood and then back into our tissues, this is called on-gassing typically. The reverse on ascent, as we start to reduce pressure surrounding us, where our tissues have a higher pressure than the pressure in our lungs and surrounding us, this is called off-gassing, where the tissues want to dissolve the gas back into the blood to be exhaled back by the lungs. If I put these on charts, this is what we're going to see down here on the bottom, where as we descend, right, the pressure surrounding us rapidly increases versus time. However, our tissues can't absorb nitrogen that quickly, or the gases in our lungs, because they've got to dissolve it into the blood. Then the blood has to carry it to the tissues, where it can be absorbed into the tissues. So this takes a little bit longer. As we spend more time on that bottom depth, or what we call our bottom time, right, eventually that tissue becomes saturated, where it slowly absorbs that gas, right, until it becomes fully saturated. At that point where the pressure of our tissues is equal to the pressure of the gas in our lungs, right, we become fully saturated. At that point, if we then decide to ascend, so for example we're at the end of our bottom time, we're going to start to come up. However, just as before when we descended, right, we can ascend very quickly and reduce the pressure surrounding us and reduce the pressure in our lungs, but the gas that's dissolved in our tissue takes a lot longer to dissolve back out into the blood, out of the blood into the tissues, back to the lungs. So we end up with higher pressure in our tissues, this red line, than in the ambient or surrounding, and this is what we call supersaturation, right? Where, again, I have more pressure in the tissues than I do in the surrounding. So if I compare them directly, right, just as we were talking about earlier about on-gassing, off-gassing, let's actually take a look at what this looks like. So on the left hand, or the Y column here, we're going to have tissue pressure versus ambient pressure, or the gas in our lungs, right? Because they're fairly accurate, or fairly similar. As we start ascent in the water column, right, as we start to dive down to whatever depth we're going to, we rapidly increase the pressure surrounding us, right? It very quickly goes up versus the tissue pressure, right? The tissues can't absorb the nitrogen and the gases as quickly, so it takes time. And eventually we reach a point where we're going to hit that bottom depth, and we're going to spend some time there, you know, searching for fish or whatever it may be. As we spend time at that constant depth, our ambient pressure, the pressure surrounding us and the pressure in our lungs, doesn't change because we're stable at that depth. However, the pressure in our tissues continues to climb as we dissolve that gas from our lungs into our blood and then into our tissues. At some point, our tissues become equal to the pressure, or the pressure of the gas dissolved in our tissues is equal to the pressure surrounding us and in our lungs, and we call this ambient saturation, right? Or tissue saturation, where the tissue pressure is equal to the ambient pressure. Then as we start to ascend, again, our tissues can't get rid of that pressure or that dissolved gases quickly, so as we ascend too quickly, we end up with a higher tissue pressure than our ambient pressure. And this is where we call, again, that supersaturation, where we're off gas and we're trying to get rid of the gas and the pressure of the gas dissolved in our tissues to reduce it back down to that equal line. So why is all this important? Well, this becomes important because if we get too supersaturated, right, where we end up with higher pressure of gas dissolved in our tissues than in the ambient or in our lungs, we can actually start to form bubbles, just like that soda, right? So if I open that soda too quickly, right, I end up with a bunch of formation of bubbles, right? Same thing happens at depth. As we descend, we start to basically put carbonation into that drink, just like that soda stream, right? We start off with less or equal amounts of gas dissolved in the liquid, and then as the gas space above, right? As we descend in the water column, we're going to inject that CO2, increasing the pressure inside there, right? And eventually, initially, the liquid's going to be undersaturated, right? The pressure of the gas dissolved in liquid is going to be less than what we're putting in. As we stay at that depth, just as we leave that soda on that soda stream, right? Eventually, the gas that we injected is going to dissolve into that liquid, and they're going to become equal or saturated, right? Then, as we start to ascend in the water column, right, that gas wants to come back out of the solution and basically form bubbles, and then come back out to the surface. Those bubbles that form are what cause DCS. And they're caused because our tissues can't dissolve the gas fast enough back into the blood, or the blood can't dissolve the gas fast enough back into the alveoli or the lungs to be exhaled. So those bubbles are the form of DCS, or decompression sickness. An important thing to think about here is what we call the M value, which we're going to talk about a little bit more later, but that's the limit of pressure differential between tissue pressure and ambient that our tissues can handle before they form bubbles. As long as we stay underneath that limit, that M value, that critical supersaturation limit, I can off gas without forming bubbles. If I go over that M value, right, just as if I open that soda too quickly, I'm going to form bubbles. Does that make sense? So moving on. There's another part to this, and that's what we call perfusion, aka blood flow, right? So some tissues have better blood flow than others. Think about the heart, the brain, the lungs, right? They have really good blood flow. Things like fat, bone, joints, they don't have as good blood flow. That difference in blood flow affects the rate at which the tissue absorbs or releases nitrogen back into the blood. So a tissue with really good blood flow will absorb nitrogen really fast because it's got a lot of blood bringing it that gas, right, or that nitrogen. And then on the reverse, as we start to ascend, it's got a lot of blood flow going through it to dissolve that nitrogen from the tissue back into the blood to be exhaled. Slow tissues, though, think like your bones, your joints, right, or fat, they don't have as much blood flow, much veins through them, especially like your bones. Because they don't have as much blood flow, they are slower to absorb that nitrogen because they've got less blood bringing them nitrogen on the descent or the bottom time. And on the ascent, as we start to come out of the water, right, they don't have as much blood flow, so they can't dissolve that gas as quickly into the blood or the surrounding because there's not as much blood flow, meaning they're slower to off gas. This is what we call half times, or rate of gas exchange. And this is important because there's multiple different tissue types in our bodies. Some things like our muscles, our skin will depend on temperature and exertion levels, but some things just solely don't have really good blood circulation, like your bones or your joints, and they're slow tissue. So knowing what tissue has the most saturation or most nitrogen dissolved into it is important to know, as well as how fast it can get rid of that nitrogen. Well, why is that important, Josh? Because we get into that limit, that M value, right? So thinking about this in another way, the half time, what we define as half time, is the rate at which nitrogen is absorbed into a tissue or until it reaches 50% of its saturation level. That's basically a rate or a measure of how fast, when I inject that pressure, this liquid can absorb that nitrogen, or that CO2 gas in this case, right? Then how fast it can release it. That's the half time, right? The M value is the limit of supersaturation, right, or pressure differential between the liquid and the ambient that a tissue can handle before bubbles are formed. This is more like how fast I ascend. So if I open this bottle really quickly, bubbles are going to form, right? It can fizz out. Versus if I open it really, really slowly, right, and ascend really, really slowly, I give my body more time to dissolve that nitrogen back into the blood and then back out the lungs, reducing the pressure in the liquid before I come to the surface. So why is this important? Because half time is important in M values because they're directly proportional. So fast compartments, or compartments with really small half times, are quicker to off gas and on gas. Because of this, they have higher M values, meaning they can take a lot more pressure differential, right, or higher tissue pressure than ambient, than slow tissues. That's because of that blood flow. So the more blood flow they have, the more blood flowing through them, right, the more chance they can push that higher pressure differential of gas into the blood, dissolve it back quickly, and then out to the lungs. Slow compartments, on the other hand, don't have as good a blood flow. Because of that, they have lower M values. That's because, again, they can't dissolve that gas into the blood as quickly because there's not as much blood to dissolve into, causing bubbles to form, just like if I open that bottle too quickly, right? So slow compartments have lower M values, or lower limits before bubbles start to form in the tissues, and fast compartments typically have higher M values. M values being that limit at which bubbles form. So now we've talked about the two factors of bubble formation, and there's a third one. So saturation level, the amount of gas in solution, right, is dependent on depth and time. So the longer I spend at depth, just like this soda stream does, the more pressure I inject in it, right? The more time I give that gas to dissolve into that liquid. That's your saturation level. For sodas, mostly from the factory, they're at a given pressure, right? The pressure differential is the difference in pressure dissolved in the liquid versus the gas, or like the gas in our lungs, right? That pressure differential relates directly to our M value, right? The bigger the pressure differential, the more likely we're to surpass that M value and cause bubble formation, right? This is directly proportional to how fast we descend or ascend and how long we spend at that depth, right? That pressure differential. And then the last one we haven't talked about yet is the amount of micronuclei. So what are micronuclei? Think of them like a little seed. So the plant grow, in this case the bubble, right, without that seed. So micronuclei are little gas seeds. They allow the bubble to grow, and then as the bubble grows, more and more gas can dissolve into that bubble, making it bigger and bigger, causing more and more symptoms. Think of this like pouring soda into a glass, right? If I pour really, really slowly, I don't get a lot of bubbles, right? And I can slowly fill it to the surface. Or if I just dump the can really quickly into the glass, I'm going to form a lot of bubbles and potentially overflow the glass, right? That's due to micronuclei. The same thing if I got to prove it to you with beer, right? Because I like beer personally. So if I take a bottle of beer and or a cup of beer and I set it on the counter, the saturation level, or the amount of gas dissolved in that beer, doesn't change from the surface to the bottom of the glass. The pressure differential between the bottom of the glass and the top of the glass is fairly consistent, very minimal difference in pressure change, even though it's a couple inches. So then why do these little bubbles in the glass get bigger and bigger and bigger as they get to the surface? That's because of micronucleation. So basically the imperfections in the glass and on the sides, the scratches, things like that, allow little seeds. Those seeds then are a site where that gas can then form a bubble. As the bubble forms, it allows more and more gas to dissolve into that bubble, making the bubble bigger and bigger. Just like that bottle or that cup of beer, as it gets higher and higher in the water column, more and more gas will dissolve into it until eventually it reaches the surface. Why is this important? This is important because of blood flow. So our blood in our veins and our arteries is constantly being shaken up as it's being pumped around the body. The more blood flow, the more micronuclei form and the more bubbles can form. So think about that again, that soda stream. A good way to think about micronucleation is this bottle's sealed right now. There's basically the same amount of pressure of gas dissolved in the liquid as there is on the surface. And yet if I take this bottle and I shake it up, just like the blood shaking up in our blood in our arteries, you'll see these little tiny bubbles start to form, right? That's just like the turbulence that's in our arteries as the blood is basically pumped around the body. Those little tiny bubbles then become gas seeds that allow bubbles to grow bigger and bigger and bigger until they form DCS type symptoms. Alright, so now we know the three ways that bubbles form. We know bubbles are the form of DCS, so what are the different types of DCS, or decompression sickness? There's two main types, decompression illness and arterial gas embolism. If I had to split them, about 75% of the time you end up with decompression illness, about 25% of the time you end up with the more serious version of arterial gas embolism. And these are directly proportional to the type of tissue we'll talk about here in a second. Decompression illness, right, is typically a small venous bubble or tiny bubble that forms in the tissue or in the blood, right, that gets basically causes inflammation or a immune system type response. So if it forms, say for example in the tissue, it can push the tissue apart, causing localized damage. Because that bubble basically pushes the tissue, you end up usually getting inflammation, swelling, redness, or rash, just like you would if you had an infection in that area. Sometimes the blood will actually attack that tiny little bubble like it would a bacteria or a virus and cause platelets or little small blood clots, right? However, then if those bubbles form in like the nervous system or in your nerves, right, they can cause numbness, dizziness, central, peripheral nervous system damage, vertigo type things if they form in the ears, or even chest pain. So these tiny bubbles, what we call decompression illness, or venous bubbles, typically form anywhere from 0 to 48 hours after the dive. They typically grow larger over time, which is why symptoms typically get worse the longer you prolong it, getting help after the dive. Some typical symptoms of decompression illness, again, these microbubbles form in the skin in particular, right? So skin tingling, numbness, especially in the joints, extremities like the hands, the feet, joint pain, right? Rash on the chest or on the skin. They can form blood clots. You'll see like a bruising type look. Things like that are symptoms of decompression illness. Now we get into the more serious version, which are arterial gas embolisms. What happens here is these little microbubbles, instead of forming all over the body, they basically form really rapid, large bubbles. These typically form anywhere from 10 to 20 minutes after the dive. They're typically a very sudden, growth of the bubble. That sudden growth becomes a problem because if they grow in the wrong spot, say for example in an artery or a vein, they can block blood flow. And when they block that blood flow, just like a blood clot, right, they starve the tissue of blood, and the tissue ends up being, dying because it can't get enough oxygen. The severity of where these bubbles form is really dependent on location. So if the bubbles form in your brain, for example, or in your neurological system, you can get seizures, you can get paralysis, altered consciousness, visual disturbance like hallucinations, right? They form in and around the heart, you can end up with cardiac issues like heart attack or stroke if they form in the carotid artery. You can also end up with pulmonary damage. So if those bubbles form in these little alveoli, right, they can actually form big enough to actually rupture these alveoli, causing damage to the lung tissue. What's really interesting is, again, as we look at blood flow and perfusion, right, we said that, blood, heart, lungs, brain, right, they have really good blood flow. Well, if we look at the symptoms and the percentage of likelihood of showing up in a DCS type case, we find that tissues with really fast or really fast half times or fast type tissues have the least likelihood of DCS symptoms. However, the slower tissues, those slow compartments, have the highest percentage of symptoms. So joints, again, low blood perfusion, right, not as much blood flow, show up 89% of the time you get DCS, you end up with joint pain. 70% of the time you end up with arm symptoms, and that's because there's not as much blood flow in the arms as, say, for example, in the legs. Hands, joints in the hands, things like that. Numbness, tingling. Leg symptoms, again, 30% of the time. And then as we move closer to the core where there's more blood flow, you end up 5.3% dizziness, paralysis, 2.3% to the brain, for example, shortness of breath, 1.6% around the lungs. Extreme fatigue, like relate to the brain or the heart, right? and then 0.2% of that collapse or unconscious, that's the brain, right? Not enough blood flow going to the brain. So again, to kind of break this down, decompression illness, little microvenous bubbles form in and around the tissue, causing swelling, kind of like an inflammatory response. Arterial gas embolism, blocking of blood, just like it would be a blood clot, causing massive tissue damage because it starves the tissue of oxygen. All right, then let's go into how our computers protect us against this. So what is that little black box in your wrist actually doing? So those little black boxes are either using an algorithm or model, right? They were developed in the 1960s or 1959 if you're talking about the SOS computer. And they're using one of two models, either a gas content model, which was developed back in 1906 by Haldane, or they're using a bubble model developed in the 80s. We're going to talk about this a bit more in depth here in a second, but basic gas content models are looking at saturation level, or the amount of nitrogen dissolved in the tissue versus your M value. And bubble models are looking at saturation level versus the bubble size, or basically how much micronuclei you have. They take in inputs such as your depth, how long you spent at that depth, how many repetitive dives you've done, and how much more nitrogen loading you have, which we'll talk about here in a second. But that's all they take into that input to put into this algorithm to figure out how to keep you safe. They do sometimes record temperature, but it doesn't actually alter the algorithm at all, or the decompression stops. They do sometimes have safety, or conservative safety factors, sometimes called conservatism. RGBM, or reduced gas bubble models, typically is a 1 to 4 on a computer. If you're using like a shear water, they probably are using a ZHL 16 compartment gradient factors, which we'll talk about here in a second. So let's actually break this down. So gas content models were the first ones developed, which we'll talk about here in a second, but they're trying to maximize tissue supersaturation up to a safe limit. That limit, or that M value, is derived from experimentation. There was a doctor named Haldane in 1906 doing a lot of testing on humans and animals and what we call Cassian dieting, where they were trying to build bridges, things like that. What he did was pressurize basically in a chamber, then rapidly either decrease pressure or slowly decrease pressure to see at what point bubbles start to form in these different tissue types. From that, he built algorithms that then tracked 6 different tissue compartments or types, right? And then he based the outcome, or changed the algorithm accordingly. If he found that tissues became damaged or had massive bubble formation, he would reduce that M value until he found that it was safe to operate in that limit. Bubble models, however, do a little bit different, right? They're going to try to limit supersaturation early in the ascent to minimize bubble growth and formation. And this is all based on mathematical models of bubble formation, right? So they're trying to think about the pressure of the bottle or the bubble, the surface tension, trying to reduce micronucleation, everything else to try to basically collapse the bubble early on. And these came about from a biology doctor named Pyle back in 1980. And then Dr. Young in 1981, and then became deep stops in the early 2000s. On the bottom here, you're going to see some pretty typical dive computer brands and what models they're running. This will become important later on in lectures if you want to just note down what you're typically running. So a ZHL, a zero Haldane limit, either an 8 or 6 compartment, right? RGBM, reduced gradient bubble model. Winkles, again, a RGBM model. Bullman, ZHL, a zero Haldane limit, 16 compartments, your typical one that most computers use today. Mirrors, you have the option of choosing both. Oceanic, again, you can choose Pelagic Z+, which is a gas content model, or Pelagic DSAT, which is a bubble model. Shearwater, again, allows you to choose one of the two. So ZHL 16, a gas content model, a VPM, or variability model, B, right, or M, or E, depending on the model. Again, gas content models, or I'm sorry, bubble models in those cases, VPM. And then Sunto RGBM. All right, so let's jump to the next one. So gas content models, let's actually look in this in depth of what is a gas content model actually doing. So this all started in 1906 with Haldane. He did a bunch of experimentation trying to figure out why these people that were doing Cassian diver, basically pressurized chambers, building bridges, kept getting the bends, right, or decompression sickness. He did a lot of research and came up with this model that said there's 6 different compartments, or 7 different compartments. Based on this, we found that as long as we keep below the M values I established from experimentation on these different tissue types, you're not going to get bent. You're not going to get decompression sickness. And the way they did that is they basically calculated the nitrogen absorbed based on half times and the depth and the time, right? And they compared that against the M value, the pressure differential in the tissue, or the gas dissolved in the tissue, versus the ambient. And as long as I stay below that limit of the M value, I don't get bubble formation, I don't get decompression sickness. That algorithm, or the mathematical models he gave, was then taken by the Navy. They took that and developed their own model in 1937 using 3 compartments. They found that didn't work for them. Developed another 6-compartment model in the 1950s. Then they took that and said, okay, now how do we make that for repetitive dives? Developing repetitive dive tables that were released in 1956. Those repetitive dive tables were taken by most dive organizations, so it's like BSAT or PADI, right? They took those dive tables, turned them into RDPs. In 1976, another doctor came about called Bullman. He took Haldane's original limits and expanded it from 7 compartments to 16 different tissue types or compartments. This is what we call the Bullman Zurich Haldane limits 16 compartment model. And then we progressed to RDP and some of the other models that came off of this, but they're all kind of based off that Bullman ZHL16 model. Again, comparing the different tissue types, each tissue basically making a mathematical model of how much gas dissolved into that tissue based on descent and bottom time, then making an M value for that tissue and saying, you know, I'm going to ascend to a safe pressure differential. In this case, you can change your safety margin and just the distance away from that M value you want to take. Right? The closer you are to the M value, the more risky the dive. The farther away if you are from the M value, the less risky. But you know, say I use a safety factor of 2 or a gradient factor, right? I can come up to a certain point where I find that pressure differential is too risky for me. I'm going to stop at that depth, say for a safety stop, right, or decompression stop. As I stop at that depth, my ambient pressure doesn't change, but it allows my tissues to dissolve the gas from the tissues back into the blood, decreasing the tissue pressure back to the lungs. And as soon as I get back to that close to that saturation where tissue is equal to ambient, I can ascend again to a safe limit or close to that M value. Then I will stop again, doing say a safety stop, something like that, allowing my body to decompress again until I can eventually reach the surface. Then came bubble models, right? So these came from a doctor named Dr. Pyle. He was a marine biologist that basically kept bringing fish from deep depths up to the surface. What he found was the fish kept dying, right? So he started dissecting the fish on the surface and trying to understand why they died. So just like a diver uses a BCD for buoyancy, a fish uses something called a swim bladder. As we ascend to the surface, we're taught to basically deflate our BCD, right? To let the air out because that gas is expanding. Well, the same thing was happening in the fish in their swim bladders. They couldn't deflate their swim bladder fast enough, so it ends up either rupturing or expanding too much, crushing their organs. So this Dr. Pyle basically found that if he took a needle and basically popped their swim bladder or released some of the gas on ascent or on the deeper parts of the dive going up to the surface, these fish had a lot higher rate of survival and being potentially used for science on the surface. He took that study and gave it to another doctor named Dr. Young in Hawaii in '81. This doctor took mathematics and then what Pyle had found, right, and combined the two to make what we call VPM, a variable permeability model, which then evolved into reduced gradient bubble model from other dive manufacturers and computer models. But basically the whole idea behind this mathematical model is we're going to stop bubble formation or reduce bubble growth. The way we do that is we're going to keep the ambient pressure high by staying deeper early on the ascent, crushing those bubbles, right, getting rid of micronucleation, dissolving it back into the blood and the tissues, so it can slowly come out over time. And then as we ascend or start to come towards the shallower part of the dive, I should have done most of my my decompression early on in that deep part of the ascent, so I shouldn't need it later on the later part. The problem is this is all mathematical, theoretical math. Nothing on experimental data or experiments were done on this to my knowledge. And in theory, it does work, right? So if you get the deep stops right, you can reduce the shallow water stops as you've clearly done or already done the majority of your decompression deep on. This became very popular with technical divers in the early 2000s and was coined the term deep stops. So again, if we look at the math kind of behind it, what they're trying to do is by staying deeper longer, basically by pressurizing and not taking that bottle of soda or beer or whatever off of that soda stream, right, and letting it sit there a little bit longer, I can crush some of those bubbles. And if I can keep the ambient pressure high enough, I can crush the bubble will dissolve back into liquid. Or at least stay the same size, right? If the bubble or the pressure surrounding it is less than the pressure inside the bubble is going to want to expand. And as it expands, right, more and more gas is going to want to dissolve into that bubble because as it expands, the pressure inside the bubble decreases, right? So more gas wants to dissolve into the bubble, increasing the pressure. So the bubble gets bigger and bigger and bigger until it potentially causes decompression type symptoms. And then mathematically, there's a point in between the two where if I keep the ambient pressure high enough, or the pressure surrounding me, right, I can keep the pressure inside the bubble constant to basically restrict or control the size of that bubble growth early on, hopefully crushing them back into solution to dissolve back until I can get them out of the blood, or out to the blood and then out to the lungs. Right. Not to be outdone though, then came what we call gas content models. So, or gas models with gradient factors. The proponents of this basically said, hey, these bubble models are really popular. They sound really good. They're gaining a lot of popularity. How do we make our gas content model similar to them? So what they found is we can modify the gas content model to be similar to bubble models using what we call gradient factors. And these gradient factors are divided into two types: GF low, which controls your emphasis or depth of the first decompression stop, and GF high, or the emphasis or the length of the shallow stops. So how does this all work? Well, just like a gas content model, they're going to compare ambient pressure, the pressure in the water column and in our lungs, versus the pressure of the gas dissolved in our tissues. They're then going to look at, okay, as I start my ascent, right, I'm going to compare it to that M value, but this time, on ascent, I'm going to put in a value of my GF low, how comfortable basically I am on the beginning part of the deepest part of the dive coming to that M value. So maybe I feel I want to be really safe, so I'm going to choose a 30% of that limit. So on ascent, the beginning part of my dive, I don't want to be more than 30% of the M value. So the computer goes, okay, I'm going to put a dot there. And then it's going to ask you, well, what about your gradient factor? When you exit the water, how close to the M value are you comfortable being? In this case, this computer shows 80, right? Or this person. So I'm going to put a dot there. Then the computer basically draws a line between your GF low and your GF high, and that becomes your new, basically, M value, your new limit. So now the computer goes, okay, as I start to ascend, I've come to 30%. I'm going to stop. I'm going to allow myself to decompress, and I'm allowed to come up a little bit higher, right? And then I'm going to stop. I'm going to decompress, putting emphasis on the deep part of the dive, right, with the gradient factor low. And then as I start to come closer and closer to the surface, kind of going back and forth until eventually I reach the surface, at which point I tell the computer with the GF high how close to the M value for that tissue compartment I'm comfortable being. To drive this home, again, the closer you are to the M value, the higher risk of DCS you are. So your low gradient factors, or your low safeties, are typically like your 45-95 if you're using a shear water. A 40-80 is kind of like a mid-range safety factor, or a 2 or 3, right? High safety, like a 4 for an RGBM, would be a 35-75, so 35% limit on initial ascent, 75% when you surface. My personal preference, or what I personally dive, is a 40-70. So I'm comfortable getting up to 40% of the limit initially on, right, or the initial part of my dive, and then I like to end the dive 70% below, or 30% or 70% of my total M value on the exit of the dive. Alright, so now we've talked about the models, we've talked about the physics, the science behind it, we've kind of really understand the how all this comes together to form decompression sickness, how those bubbles can interact within the body to give you different symptoms, whether decompression illness or AG or arterial gas embolisms. Now let's talk about factors that affect decompression sickness. So I really want to drive home, there's a lot of things your computer doesn't track that can affect your risk of DCS, and which we're going to talk about in depth, a couple of them here in a second. But basically your computer only tracks breathing gas, so the percentage of oxygen and nitrogen in the gas you're breathing. If you're doing how many dives you've done recently, or how much repetitive dive you're doing, the atmospheric pressure at the start of the dive, at the end of the dive, the maximum depth you went to, or the depth of all the different, the dive portion, right, or your profile, if you will, how long you spent at those depths, if you did any stops, and how fast you descended or ascended, right? More focused on the ascent rate. All this your computer tracks. However, there's a whole bunch of other things your computer doesn't track. Like, what if you exerted yourself on that dive? If you're exerting yourself, right, that's increasing your blood flow because you're trying to work. Maybe you're trying to keep yourself buoyant, or maybe you're trying really hard to fight a current or a drift, right? And how long you did that, that all affects your nitrogen absorption, because increased blood flow, increase of nitrogen absorption, right? Your thermal status, if you're cold or warm, and how long you were cold or warm, has a factor in decompression sickness. Your predisposition, so your state of hydration, how much blood you have in your body, and how liquid it is, right? The more dehydrated you are, and the more thicker the blood, the less it can carry gas. The more fluid or hydrated you are, the more liquid in your body, right? The more it can dissolve and flow between tissues easier. Your physical health or fitness level, right? Your age, if you've had a history of decompression sickness, that could put you at more risk. Your body's action, we'll talk about here in a second, can have a huge impact. Your circulatory rate, maybe you don't have a high blood flow rate. Maybe you have something wrong where you have high blood pressure, something like that. If you take any drugs, that can have a huge impact as well. Even your genetics or epigenetics, so this is common in what we call PFO, or a hole that allows blood to flow from the left right to the right side of the heart. This could have a factor on DCS, we've seen. Or even the last part, your acclimatization. So just like an athlete works out every day, is able to lift more and more weight, right? without less and less effort. Your body does the same thing. If a person dives a lot and goes through a lot of decompression type stress, their body can actually build up a tolerance to that and allow them more and more decompression without actually getting symptoms. So acclimatization, or how much you dive, can actually have a factor as well. So first thing our dive computer does track but has a huge impact is what we call the dive profile. This is probably one of the biggest things when you're talking about decompression sickness. So doing something like a sawtooth profile is very, very bad. What do I mean by a sawtooth profile? Well, that's basically ascending and descending a lot on a dive. So say, for example, you dive down, you want to go look at something, and you see something above you. So you quickly ascend to go take a picture of that. And then you see something back down the bottom, maybe a wreck, or your buddy's calling you out. So you quickly descend again, and then you ascend again, you descend again. What's happening is you're forming little bubbles that don't have a chance to decrease inside, so they grow bigger and bigger and bigger on this sawtooth profile until they start to have symptoms of DCS. That's really, really bad. So you want to try to avoid sawtooth style profiles. You want to kind of get down to the depth you're at, and then slowly, get shallower through the end of the dive. How long you spend at that depth, the duration, how deep you go also has a factor. So the deeper you go, the more pressure differential from the water column pressures, and the higher pressure gas you have to breathe. The higher pressure gas means more nitrogen dissolves into the blood and into the tissues, right? Until you become saturated. So again, depth and how long you spend at that depth, how long it takes for those tissues to become saturated, how close they become saturated, has a huge part in this. If you're doing repetitive dives, and how long you spend on the surface between dives has a huge factor. Well, what do I mean by that? Well, just as we talked about earlier, you can start your first dive saturated, or as you descend, you start to build up some nitrogen. As you're down along the bottom, you basically start to ascend, and when you reach the surface, a lot of your slow tissues will still have nitrogen dissolved into them, right? This just doesn't go away. It doesn't just magically disappear. So this nitrogen that's still dissolved in your tissues, even if you have no symptoms, it's still there. You still have a pressure differential. If you don't do a long enough surface interval, you could begin the second part of the dive with some nitrogen residual still dissolved in that tissue. Then you do your second dive, and upon exiting that dive, you have more nitrogen that's not come out of those tissues, so you end up with a higher amount of nitrogen dissolved in those tissues on the surface. You get closer to risk of DCS. Then you say, you know what, I really want to go again. I don't want to spend a long time on the surface, so I'm going to dive again. And as you dive again, you're going to build up more residual nitrogen dissolving into your tissues until you surface again with potentially a very large amount of nitrogen dissolved in those slow tissues, putting you at high risk of DCS. So these short surface intervals, you got to think a slow tissue, sometimes the half times 120 minutes or 240 minutes, so up to 2 to 3, 4 hours to fully off gas, if not longer in some cases. That's how long some of these surface intervals will take to get rid of all the nitrogen. Again, so if you do a short surface interval, say 30 minutes or 20 minutes, you're not getting rid of all that nitrogen. That continues into the next dive and keeps building in those slow tissues, putting it more and more risk. Ascent rate, we talked about a little earlier. Let's really drive into it. What do I mean by ascent rate? It's basically how fast you come up from depth until you reach the surface. 60 feet per minute is the recommended PADI ascent rate. I believe most agencies also recommend 60 feet per minute, but what I find really interesting is in 2009 there was a study published by the Journal of Aviation, Space, and Environmental Medicine where they took a bunch of divers, 47 in this case, and they put them in a pressure chamber, and then they put a ultrasonic basically sensor or device on them looking at the blood, right? And inside the blood they could see the formation of bubbles. And then they basically in this chamber took the divers and either took them at a 60 feet per minute ascent or release of pressure, or a 30 feet per minute release of pressure. And what they found is the ones with the 30 feet per minute had almost half the risk or half the bubble formation as the ones at 60 feet per minute. Kind of fascinating, right? So the ones who ascended, twice as slow at the 30 feet per minute, half the risk of DCS versus those that ascend faster. So why does this become important? Because we get into what we call safety stops, right? So safety stops were developed in 1988 by PADI, and they were developed because even though people were following the dive tables, we still end up with a high chance of DCS or decompression sickness. What they found though is the ones who had a lower chance of DCS spent basically a short amount of time along or at a certain depth, or at a shallow depth, allowing their body to decompress. And this kind of makes sense. It's kind of the same theory here, where as you ascend, you reach too close to that end value, you stop to let that gas diffuse back into solution, back into your blood, and then be basically exhaled. Same thing happens when you do a safety stop. You're allowing your body to stop for a minute, release some of that built up pressure differential between your tissues and your blood to dissolve that gas back in the blood. Then that blood has a higher pressure than what's in your lungs, so it dissolves back in the lungs, allowing you to safely off gas, right? So the longer you spend on that safety stop, the more time you're giving those slow tissues, for example, time to fully off gas, and the less risk you are DCS. So this brings up why not do a 5 or a 7-minute safety stop. Comparing dive models, right? So I get this a lot, technical questions of which model is better. I'm not going to give you my personal opinion, but I do want to give you a recent study, and you can form your judgments off of that. 2011, the Navy Experimental Dive Unit, NDU in Florida, did a study. The whole purpose of this study was the outcome had to be decompression sickness, the formation of large bubbles and decompression-like symptoms. What's fascinating is those with a shallow stops profile, they compare basically a gas content model or a shallow stops profile versus a deep stops profile or a bubble model. Those that basically dove with the shallow stop or the gas content model, only 3 out of 192 divers ended up with decompression sickness. Versus those that followed the bubble model, right, or the deep stops model, 10 out of 198 people ended up with decompression sickness. So almost 3 times the amount. That's a crazy difference. Not only that, but then they compared using ultrasonic, again, sensors, the size of the bubbles in the blood. So 0 being no bubble formation or very, very tiny venous bubbles, and as they get bigger and bigger and bigger until you get to 4 and 5 grade, or 3 and 4, I'm sorry, that can form these arterial gas embolisms, right? What's fascinating is shallow stops, they're kind of broken out evenly. You do have a little bit more of grade 3 than 4, but a decently even distribution. Deep stops, however, have a fairly large amount of grade 4 or the worst case bubbles 3 and 4 versus grades 1, 2, and 0. Very interesting. So why does all this happen, right? Well, what comes into play here is bubble models don't always take into account these slower tissues. So what they did in this study next is they compared fast tissues versus slow tissues on the left side, right, versus bubble formation in the blood. Bubble forming is usually this green color. As it gets bigger, the yellow color, red being, or orange being a little bit bigger, and then red being a fairly large bubble. And then as the tissue still begins to, or basically absorb nitrogen, that's this blue. If it's absorbing less nitrogen, it's the purple, and then black's no bubble formation. You're kind of in a saturated state. What they did is they then compared the two profiles. So those doing the deep stop, right, they found that the fast tissues do have less supersaturation early on, right? By doing those deeper decompression stops versus shallow water stops, they did get rid of bubble formation in the fast tissues. However, they didn't take into account the slow tissues. So the slow tissues at these deeper depths, even though the fast tissues are off-gassing, the slow tissues haven't fully reached saturation. So they're still taking on gas. They're still on-gassing, right? They're still dissolving gas from the blood into the tissue. So this becomes a problem because the theory behind deep stops is you've done most of your decompression early on in the deeper parts of the ascent, so you shouldn't need as much emphasis on the shallow part. But what we found is these medium and slow rate tissues end up with massive bubble formations at the point of surfacing, or very, very, prior to that, especially along the fat or the slow tissue. So that is an insane amount of bubble formation. Again, kind of leading into why you had more instead of DCS versus deep stop versus shallow stop. Comparing that, right? Well, in the shallow stops, I do get a lot more bubble formation in the fast tissues because I'm quickly ascending, not giving these tissues enough chance to off-gas, but there's a trade-off. While I do have more bubble formation and pressure differential in the fast tissues, those tissues typically have a higher end value. Because they have a higher end value, they can take more critical supersaturation and bubble formation before it becomes a decompression type system or symptom. Versus the slow tissues, right? They, by ascending quickly to a shallower depth, you stop them from on-gassing and absorbing nitrogen, so that as you do your safety stops at these shallower depths, they can off-gas more slowly and get rid of that gas, so you get less bubble formation on the shallower stops, and then at the point of surfacing, you get a lot less bubble formation in the slow tissues and nothing in the fast tissues. So a lot less incidence of DCS. Kind of interesting, so I'll let you make your own conclusions on that. Next one's physical health, and your computer does not track this, but let's really be honest. Diving is a very physically demanding sport. If you think about the two most common types of diving, you're either jumping off a boat, or in a lot of cases you're going through waves, current, you're carrying a lot of heavy gear, potentially to and from the dive site, or climbing up and down a ladder. There could be a lot of current if you're current diving in Cozumel, Japan, anything like that. But even the act of breathing a pressurized gas, your lungs have to work harder and harder basically just to breathe that pressurized gas at depth. And the higher the pressure, the more they have to work. So poor physical shape definitely puts you at higher risk of DCS. We're going to talk about that in a second, more about physiology. But poor physical shape also leads to higher fat tissue. Higher fat tissue we know is a slow tissue. The more slow tissues you have, the higher risk you are of DCS because they don't off-gas as quickly. Dehydration comes apart, right? The more dehydrated you are, say for example you're drinking all night before the dive, you're dehydrated. Because you're dehydrated, you have less blood in your circulation, right, or thicker blood, both leading to higher blood pressure and less blood circulation, not allowing your body enough blood to basically off-gas and on-gas, potentially putting it at higher risk. Age also becomes a factor. The older you are, the more risk you are for DCS. And then the last one's stress. So the more stressed you are, either in and out of the water, stress we know can build up higher blood pressure, can lead to higher blood, heart rates, things like that. That all affects you, right? The higher the blood rate and blood pressure, the more you're at risk for micronucleation, the more you're at risk for more gas being dissolved into the blood. So the higher blood pressure, the more gas can dissolve into it, things like that. So physical has a huge impact on your risk of DCS. The more physical and in good shape you are, the better off you are, the less risk of DCS. The less physical shape you are, the more poor your physical shape, the more at risk you are for DCS. And this plays right into the next one of exercise or exertion at depth. So the timing and the intensity of how much your workload or your exercise at depth has a huge factor on your risk of DCS. Well, why is this? Because exertion increases blood flow, and typically blood pressure as well. By increasing blood flow, you increase the amount of gas being carried to the tissues from the lungs. You increase basically the gas carrying capacity of the blood. So more gas is then being carried to the tissues, where more gas is absorbed by the tissues, putting you at higher risk, higher levels of saturation, potentially higher risk of decompression sickness. Now the reverse is also true. Some mild exercise during the decompression steps or stops on the way up could potentially reduce your speed up your off-gassing, because again you're increasing your blood flow. So it could be a good thing, but the problem is if you exert yourself a lot in the deepest part of the dive, you're increasing the amount of nitrogen you're absorbing, increasing the amount of saturation, putting yourself at higher and higher risks. And then too much of a good thing can also be a bad thing. So after diving, you really should avoid exercise as long as possible, and that relates back to those micronucleation. So if I come out of the water, right, and I'm carrying a bunch of heavy gear back on the boat, potentially fighting waves or current, trying to drag myself up onto the boat, that's exerting myself. And when I exert myself, just like that soda stream, I'm starting to shake up the blood and form micronuclei. Those micronuclei, right, start to form little bubble seeds, right, that then grow bigger and bigger and bigger the longer I'm out of the water, putting me at higher and higher risk of either decompression illness or arterial gas embolisms. So you really should avoid exercise after the dive for as long as possible. If exertion is unavoidable, say for example you got a shore dive and you got to carry your gear back to the car, or maybe you got to fight through the waves and the currents to get back to shore, then dive more conservatively, right? Reduce the depth, reduce the time you spend at depth, just try to minimize your risk of decompression illness. Maybe spend longer at your safety stop, for example. So again, exercise has a huge risk or a huge factor in decompression sickness and decompression risks. Next one I want to talk about is thermal exposure, right? Looks like my beagle's joining the video. Thermal exposure. So there's an actually recent study in 2007 done again by the Navy Experimental Dive Unit, where they compared cold water, basically thermal temperature, water temperature versus the dive, and they kept the pressure and the decompression model identical between the two. They used the Navy decompression tables explicitly, and they maximized the depth and times of those depths in this particular study. But what they're trying to understand is what is the effect of the water temperature, body temperature on decompression illness. This is a really, really important dive study because they had some really interesting findings. So the highest risk scenario, where you start the dive warm and you end up cold, so majority of divers or dive just like myself, where you're starting the dive warm, you're in that nice wetsuit, water slowly gets in, you slowly start to cool off throughout the dive until you eventually get cold. Well, on the warm part, you're maximizing your nitrogen absorption because you have really good blood flow, right? You're warm, things are pumping good, you may be exerting yourself, for example, but you're warm. So extremities, your skin, your muscles, things like that are good. They have really good blood flow, really good absorption of nitrogen. But then as you get colder, blood tends to pull away from your extremities, your skin, your muscle, and back to the core, minimizing blood flow, which then minimizes your ability to eliminate that nitrogen from those tissues and dissolve it back into the blood, increasing your risk of decompression sickness. So in this particular case, they found that if you start the dive warm and end the dive cold, you ended up with a 30-minute bottom time at 120 feet at 22% chance or 22% risk of decompression illness. That's huge. 25% of the divers in this case got decompression sickness after only a 30-minute dive at 120 feet. But what if I start the dive cold and I end the dive cold? Well, again, if you start the dive cold, you're minimizing that blood flow, so you minimize nitrogen absorption. And because you're cold on the exit, you also minimize your elimination. You kind of equal, if you will. So here they found that doubling the bottom time was basically the same incident rate or 22% chance of decompression illness. That's really fascinating. So if you start the dive cold and end the dive cold, I could double my bottom time with the same chance or risk of decompression sickness. Well, then that brings the question, right, at least curiosity-wise, what if I start the dive warm and end the dive warm? Well, then you maximize your blood flow starting the dive, you maximize your blood flow at the end of the dive, so you kind of end up with this cancellation effect where you have really good elimination of nitrogen on the exit or the ascent part of the dive. Here we end up with a 70-minute bottom time with only a 16% chance of DCS risk. Really fascinating. Then the lowest risk is if you actually start the dive cold and you warm up throughout the dive. So because you're cold initially, you minimize blood flow, minimizing your nitrogen absorption. And as you warm up, you start to increase blood flow, especially the extremities, the skin, the joints, things like that. By increasing that blood flow, you increase the amount of, or ability of those tissues to get rid of the gas, pushing it back into the blood. And then here we end up with a 70-minute bottom time, but only 1.3% of those ended up with decompression type symptoms. Insane, correlation here. So even for myself, I found this really fascinating. Most of my dives, I start out warm and I end up cold. I mean, that's just part of diving, right? But that's putting me at the highest risk of decompression illness versus starting the dive cold and ending up warm. And this plays a huge factor in, especially when you consider the temperatures they are playing with. So their cold water was 80 degrees Fahrenheit. I would consider that warm water. I would consider cold, 55 degrees or even colder, 30, 40 degrees on some of these clear water, deep lakes where you're diving at depth on technical wrecks or historical sites. 80 degrees is not that cold, but yet had that big a factor versus their warm water, 97 degrees was, 90, that's like bathtub water. So again, when you start really thinking about this, probably would have had an even bigger impact if we were comparing, cold water versus coming up to the shallower water depths and warming up quickly. Really think about those as we start to get into this. So temperature, thermal exposure, what you're using, what wetsuit, whether you're driving a dry suit or not, all that plays a huge factor. The next one I want to talk about is narcosis. So what is narcosis? Narcosis, or nitrogen narcosis, is an aesthetic drunk feeling underwater. Its symptoms can include feeling of euphoria, a shortened attention span, inability to concentrate, a feeling of anxiety, and this is basically because of nitrogen loading in the central nervous system. Basically, the nitrogen dissolves into the nervous system, interferes with cell-to-cell communication, causing you, again, these types of symptoms. How narcosis occurs is directly proportional to decompression sickness. So the deeper you go, the more at risk you are of narcosis, especially past 60, 80 feet. And the longer you spend at that depth, the more you're at risk of narcosis. The factors that raise your risk of DCS also seem to raise your risk of narcosis. Well, why does that matter? Because narcosis can have a huge impact on decompression sickness. It compounds, basically, because you start to develop an inability to focus or inability to concentrate, which makes it harder to think about rationally, what do I need to do on this dive to reduce my DCS risk? You end up making more or less responsible decisions at depth, increasing your risk of decompression sickness, and potentially, decompression serious, illness. Well, you say this never happens, right? As long as I know what I'm doing, I shouldn't get narked, and if I get narked, it'll be fine. It's just a feeling, inability to focus, right? This can compound in a very, very bad way. And I'm gonna give you an example. I was guiding a group, right? In this case, my dive buddy was another dive master. We were taking this individual to a wreck at about 120 feet. Both of us were decompression procedures trained, TISDI, right? So we both understood fully narcosis. We fully understood decompression theory. We went through the dive plan. We fully understand what we were doing. We had agreed upon everything, right? We're gonna drop down to 120 feet, spend a couple of minutes along this dive, and then slowly start our decompression stops on the way up. But for some reason, as we were starting to descend, we hit the bottom, or close to the bottom at 100, 110 feet. I turn around, this diver's starting to panic, right? This dive master. By the time I started swimming towards them, and they were only a few feet away, they decided to basically panic and bolt to the surface. Luckily, I was close enough to them. I was able to chase after them, catch them, right? I dump both our BCs, stop this about 50 feet, and by that time, by that ascent, right, the decrease in pressure decreased the effects of narcosis, and this dive master came to their senses, kind of realized what was going on, and we were able to make a safe ascent from that point. But this would have been a really risky situation. So when I got back on the boat, I kind of started asking this dive master, like, what happened, dude? Like, we were going good, and all of a sudden you just panicked, and you did a rapid ascent to the surface. If I hadn't stopped you, you could have gotten bent really, really easily. But this dive master explained, like, I don't know what happened. I was all good, and then as I got towards, the bottom there, I just panicked. I don't know what happened. I just need to get to the surface for some reason. So that symptom of narcosis, that feeling of anxiety and inability to concentrate, compounded, right? That feeling of anxiety made him panic. The inability to concentrate or focus meant he didn't think about his decisions rationally, right? Or his or her, I should say. And he did a rapid ascent to the surface. Because of that rapid ascent, he put himself at risk of decompression sickness, potentially, having some serious implications if we hadn't stopped him on the way up. So again, narcosis can have a huge effect on your risk of DCS. Another one is what we call nitrox. Nitrox is kind of regarded this miracle gas, and in a lot of ways it is. What is nitrox? So let's understand, basically it's a higher percentage of oxygen in your breathing gas. Typical air you're breathing from anywhere around the world is 78% nitrogen, 21% oxygen. Nitrogen, or nitrox, is made by adding a higher concentration of oxygen into that breathing gas, reducing the percentage of nitrogen. By reducing the percentage of nitrogen, I have less nitrogen breathing in my lungs, which means I absorb less into my blood and less into my tissues, thereby reducing my risk of basically decompression sickness and nitrogen loading. However, this has a trade-off, has a dark side. By breathing at a higher pressure gas, or that higher pressure of oxygen, higher percentage of oxygen, we put ourselves at risk of what we call CNS, or central nervous syndrome, as well as oxygen toxicity. And typically, if you have an episode of a central nervous syndrome, you end up having a seizure underwater and very, very easily drowned. And the effects of this oxygen toxicity are very, very rapid. It's almost a logarithmic curve. So I'm not getting into all of it, but basically there's a thing called max operating depth. You'll learn in your nitrogen or advanced nitrox course, where the higher the percentage of oxygen, the less deep you can go before putting yourself at risk of oxygen toxicity. So if you think your most common blends, your 32%, your 36% nitrox, 32%, you basically halved the maximum depth. So 21%, I can go down to 186 feet, no problem. Lower risk of nitrogen toxicity or oxygen toxicity, versus if I take 32%, now I'm only be able to go down to 111 feet. That's almost, a little over half the depth. That's at risk. And then if I go to 36%, again, sounds good. I'm going deep. I want more, oxygen. I want to reduce my chance of decompression sickness. That's true, but then now I'm putting myself at high risk, beyond 95 feet of oxygen toxicity and potentially a seizure underwater. So again, while nitrox is an amazing gas, I highly recommend it if you're doing a lot of repetitive dives or liveaboards, things like that. Understand it has a caveat of limiting your maximum operating depth. So really pay attention to that. And this isn't like you magically have a seizure at past 95 feet. It's a time at depth equation as well. So the longer you spend at that depth, the more likely you are to have oxygen toxicity, just like nitrogen loading. The more oxygen basically damage you do to your cells because you're absorbing higher percentage of oxygen. So be careful and be cautious of that. This brings me to the last point, your dive buddy. So this is a really big one, but the actions of your dive buddy can directly impact or influence the outcomes of shared activities. And that's a really big way to say that, but what I'm trying to get at is what your dive buddy does has an impact on what you do. So if you think about, if my buddy has an emergency ascent, right, I'm typically going to try to follow after and try to potentially save them, or maybe they're a panic diver and we got to do a rapid ascent to the surface to prevent them from drowning, especially if they're spinning their regulator out or if they're in an out of gas type situation. That can have a rapid ascent that puts me at high risk of decompression sickness. But there's some other things as well. So what if I'm a faster swimmer than my buddy or my dive buddy? Happens all the time. Myself, I'm 6'1", I'm a really fast swimmer, been swimming all my life, right? So to me, what is a normal pace is super fast for someone like my wife, who's 4'10", has a lot harder time keeping up with me. So what maybe a leisurely kind of relaxed pace for me, she's kicking like crazy to try to keep up with me, exerting herself. That exertion puts her at higher risk of decompression sickness, and then increases her chance of being, injured. So think about those types of things. The other part is a risk taker. So a lot of times, the more experienced you are, the more likely you are to take risks. This doesn't happen just randomly, but Typically, it's a whole psychological thing. The more times you get away and the more risky you do something, the more times you get away with no incident, the more likely you are to push the envelope and take a more dangerous, a more risky approach to doing something underwater. And the more you do that, while it may be safe for you, maybe it's not so safe for your dive partner. So, where I may dive at depth all the time, past 120 feet, because I'm a decompression type diver, technical diver, maybe that's not so safe for my wife. Even though she does have some certifications to dive at those depths, she doesn't have as much experience. So what may not seem very risky to me could be very risky for her, especially if you're talking about like penetrations into wrecks where panic could involve, or loss of visibility, a silt out, something like that, or cave. That has a huge factor. So the actions of your dive buddy could have a huge impact on you. Peer-to-peer pressure has a big part of this as well. So I'm a firm believer anybody should be able to cancel a dive for any reason at any time. And this could be a multitude of reasons, but that peer pressure really starts to play a factor, because a lot of people won't cancel the dive, even if they're not up to it. Maybe they're feeling sick, maybe not well, because of what they would perceive as a loss, either financial or social. They don't want to lose the money they spent for this dive, or they don't want to be the outcast on the dive, right? And be that gun that's always canceling dive. So this comes up on the boat all the time when I'm guiding, where someone may not feel up to that. Maybe they're sick. Maybe they've got some sinus issues, for example, from diving multiple days, or allergies, whatever it may be. This can have a huge impact on the dive, especially if you're thinking about seasickness, things like that, where what if you get a reverse block? Where now I've got to spend time at depth longer with you trying to get rid of that reverse block, potentially expending a longer duration at depth, putting myself at higher risk of decompression sickness. Maybe I've got to go, you've got some issues and you're not able to equalize, or all this can lead to a panic, and now I have to do rapid ascent with somebody trying to save them. That again could have been prevented if they'd said, hey, I'm not feeling well, I've got some sinus issues, I'm going to cancel this dive. What if you're stressed out about the dive? I'll go back to, say, for example, a dive in Egypt where we purposely did this dive looking for sharks. I was super excited looking for sharks. I love to find sharks underwater. My wife, not so much. She hates finding sharks underwater, and she was stressed out about it. Her stress led to a higher blood rate, or higher blood pressure, and higher blood flow rate, higher heart rate, that then puts her at higher risk of DCS. Well, I may be excited and kind of swimming out looking for these sharks, right? She's getting stressed out thinking, oh my God, is there a shark right around the corner? You should think about those types of things, and now we have to limit our depth, limit our duration, right? Trying to be a little more preventative and cautious about that to lower our risk of decompression sickness. And this plays into a lot of part on the boat where I've seen, if you have a lot of technical or advanced experienced divers on the boat, the youngest or the less experienced will try to exaggerate skills or experience to fit in. I even found people trying to lie about their certification level so that they could go on deeper dives, because they want to be cool, they want to be part of this technical group. They want to go look at this wreck like everybody else, but they don't have the skill set to do so. So, worst case, say, they lie about their certifications and say they're experienced cave diver or wreck penetration. They go in, with this experienced group to go into a wreck potentially. You experience a silt out, they panic. That panic now puts them at risk of running out of air, which could lead to a rapid ascent. Definitely a faster heart rate and higher blood pressure, so definitely more exertion, risk of micronucleation in the blood, risk of nitrogen absorption, usually at the deepest part of the dive. Not so great. And now they're actually putting everybody else on the dive at risk because they potentially have a silt out, and now everybody else has to spend longer at depth finding their way out of this wreck. So all of that because they want to be cool and trying to fit in on the boat, either experience or skill-wise. So really pay attention to that. Don't exaggerate skills or experience. Try to fit in. It puts everybody else at risk. And even if you do have experience, are you up to date on your training? And I've seen this on a boat as well, where I actually had a gentleman really against nitrox, even though he was certified in it. I had a couple of people on the boat that were diving nitrox, and he was telling them, like, that's a voodoo gas, you're going to kill yourself, and really, kind of getting agitated about the fact these people were diving nitrox. So I sat him aside, kind of talked to him, trying to understand what's going on. Come to find out, he was trained back in the 80s, and we started talking about it. Well, back then, this type of nitrox was actually considered, there was a whole voodoo gas type, perception around it, because they didn't understand why people were seizuring and having these issues underwater. They thought it was due to decompression sickness or something to do with the gas, the nitrox. And in fact, it did. It had to do with oxygen toxicity and central nervous syndrome, but we didn't understand that at the time. Now, with more advanced training and more studies and everything else, we understand the risk of oxygen toxicity and central nervous syndrome, so we can accommodate that by limiting our maximum depth and duration at that depth, so we can dive safer on nitrox. And there's a lot of benefits to diving nitrox. And I explained this to him and kind of went through it all. But had I not stepped in and kind of talked to this individual, this experience he had of, diving, and how this nitrox was the voodoo gas, he never needed it before, and if you dove deep and could have influenced these other divers potentially not drive nitrox, potentially putting them at a higher risk of decompression sickness, sharing of bad information, if you will. So always be open to new information on the boat or even out on the dive sites, right? I don't know everything. I don't pretend to. There's always new studies coming out. I mean, a lot of the studies we're going to talk about today or have talked about are recent, in the last 10, 15 years. So while someone may have trained in the past, if you, tend to see this type of information, let's share that information out and try to bring everybody up to the same standard. And then the last part, divers tend to delay asking for help if they're experiencing decompression type symptoms or decompression sickness type symptoms. And that's because of this stigma or this perception, right? That divers who get bent or have decompression sickness messed up somehow. They must not follow their computer. They did a rapid ascent. They screwed up somehow, spent too long at depths, whatever. That's why they got bent. Well, sometimes there's not a reason why you get bent. There's a lot of things your computers, we know now, doesn't track that could lead to decompression sickness. There's a really famous diver who is another YouTuber, Divers Ready. I highly recommend him. He's a technical diver. He's a technical dive instructor. He's done thousands of technical dives on rebreathers and above, right? Multiple gases, extended range, all of that. Yet on one of his dives with other technical divers, he ended up with decompression sickness. He followed the rules. He obviously is very experienced in it. He knows the limits. He followed his computer, all the rules, followed the dive plan, everything else. Even everybody else on the boat agreed he did. Other technical divers and instructors, yet he ended up with decompression sickness. Even he admitted on the boat that, there's no way I got bent. There's just something wrong. So he delayed his asking for help, which luckily he was an instructor. He recognized the symptoms and asked within a few minutes for help on the boat. But this stigma, this perception that divers that got bent, somehow screwed up, costs a lot, because when you delay asking for help, especially if you have these DCS type symptoms, maybe you convince yourself that tingling in your hands because you're cold, or that pain in your joints because you're old, or maybe it's a previous injury, or whatever it may be. Those are key symptoms we as dive professionals on the boat need to know so we can provide emergency aid. If you have a symptom, please let us know so we can give you emergency oxygen and potentially rush you back to the hospital or a chamber, potentially save your life. This whole perception and stigma around the divers that get bent somehow screwed up, it needs to go away. There are undeserved hits, meaning you did everything right, you followed your computer, you followed all the rules, and you still got bent. It happens. And also the perception, the stigma that, this is a really big cost. And I've seen this on boats where, a diver's potentially seeing or even admitted to symptoms, and they don't want to go to the hospital because they don't want to get bent. They don't want to pay the cost of going to a chamber. Maybe they don't have dive insurance, whatever it may be. So they prevent or don't go to get emergency medical help, and they end up with massive symptoms, potentially life-changing symptoms and conditions later on. So again, this perceived financial loss leading to not asking for help or delaying them asking for help on the boat. The faster we know you have symptoms, the faster we can get you on oxygen, the faster we can get you back to a chamber, potentially save your life. And then I'm going to close this all up, kind of final thoughts on this. So what is our priority on dives, right? Are we looking for the shortest decompression time? I find this is like the race to the surface mentality where, again, I'll be guiding a group of 4, 6 divers, whatever it may be. And it seems like everybody's on a race to get back on the boat. Like you get an award for getting back on the boat the fastest, versus myself. I'm all good spending a couple extra minutes at a safety stop, right? I typically wait till everybody else is back on the boat before I surface, just trying to be the helpful dive master and guide, taking care of my divers. But those that race back on the boat, I can't tell you the number of times that they've missed out on dolphins or turtles or barracuda, whatever it may be. It's swimming by. A lot of times these extra few minutes I spend at the safety stop, right, are where I see the most, have these amazing, interactions of swimming with dolphins or swimming with turtles. A lot of it happens at shallower depth. So think about that. What's an extra few minutes at the safety stop? What's the worst that can happen? You're going to see something amazing. The other part of this is getting warm right after the dive. And this goes back to warming up your blood and that thermal exposure, right? I understand. I dive a lot in California. It's cold, especially even technical dives coming out of the water, super depth where it's 35, 40 degrees. You want to get warm fast. You're freezing, right? The faster you get in that hot shower, the better it feels. But then that puts you at higher risk. So when you get back on the boat and you immediately go to that hot shower, you immediately warm up your body, you increase your blood rate, increasing your risk of micronucleation, putting yourself more at risk of decompression sickness. What's be better option is maybe sitting on the bench, take off your gear, wait a minute, let yourself slowly warm up before you get into that hot shower. The other part of this I see a lot is struggling with wetsuits. Nobody likes wetsuits, nobody likes dry suits, right? While they have a huge benefit keeping you warm on dives, I understand they're hard to move in, especially dry suits. You know, they can be very cumbersome and limiting of movement, especially thick gloves, things like that. I understand the struggle with them. I do it myself. But that's what keeps you warm on these dives, and by staying that thermal regulation constant, you put yourself at lower risk of decompression sickness. So really think about on the dive what's worth more. A little bit of fighting that wetsuit, or waiting a little bit longer to get in that hot shower, or getting decompression sickness. What's a higher priority, right? Next one, exertion. So swimming to get that picture of that, see that object, right? So this happens a lot. I'm just as guilty as everybody else. So you're swimming along, you see a turtle or a shark, whatever, and you want to go get that picture, right? Happens a lot in Cozumel when I'm drift diving, where I have to fight the current to go get that picture. Is that picture really worth it? By exerting myself really heavy, and typically it's only for a short amount of span, and usually the deepest part of the dive, I'm putting myself at more risk for decompression sickness. And the same happens where I've seen, we'll dive on a wreck, and some of the newer divers, they're limited at 60 feet, but they've got to see that object. So they swim down really hard, potentially to currents around wrecks, or even worse, high depth or deep depths, putting themselves at risk for that picture, that object, to get that cool picture. You're putting yourself at more risk, guys. Really think, is that picture, is that object, is that experience really worth it? Or do you want to come back to it maybe later with some more training and experience and be a little bit safer about it? Then another one, being cool and being part of the group. Well, I 100% agree with, I want to be part of a group. I want to be seen as cool. I want to be that dude, right? But sometimes I've seen this turn for the worst on boats, where I've seen a lot with technical divers where they peer pressure somebody to reduce their safety factors on their computer because they don't want to spend as long with decompression stops. I get it, right? Typically these deep, decompression type dives, you're spending a large amount of time on safety stops or decompression stops. It's cold, it's boring. I get it. But by reducing your safety factors, you get out of the water faster and you have shorter stops, but you're putting yourself at more risk. And while that may be okay for you, for example, I do a lot of deep decompression type dives, technical dives, right? I could probably be more acclimated. I could probably handle a little more decompression, bubbles and formation than, say, my wife, who has less experience diving at depth, who doesn't do it every weekend or every week. And she could be at a lot higher risk. So while that lower safety risk may be okay for me, there may be other factors, like we talked about, physical health or genetics or acclimatization, all that maybe that person needs to have a higher safety factor to keep them safe from decompression sickness. Don't push or pressure those people to reduce their safety factors. There's a reason they have them. And then the last kind of priority on dives is time in a chamber can easily be $40,000 to $60,000, right? And this isn't so much a priority on the dive, it is after the dive. But a lot of times I see people, I don't want to spend money for that Dan insurance. I am not endorsed, not paid by Dan, any of those, right? But I do have Dan insurance for me, myself, and my wife, and any of my friends that I can convince to get it. And the reason for that is I've seen a lot of times on boats or guiding, things like that, where somebody with Dan insurance is much more likely to ask for help and report their symptoms than somebody without Dan insurance. It all goes back to that perceived financial loss, right? Nobody wants to spend $50,000, $60,000 spending time in a chamber for medical help. If you get Dan insurance, it's $100, $120 a year, whatever it may be. I don't remember off the top of my head, but it could save your life, because by getting that Dan insurance, that person's much more likely to report their symptoms on the boat. When they report those symptoms, they're much more likely to get medical aid and the right medical assistance, potentially saving their life and potentially stopping lifelong issues or problems resulting from decompression sickness. I've seen studies and incidences where somebody didn't get treatment because they didn't want to pay for that chamber, didn't have Dan insurance, whatever, and they end up with paralysis, potentially in a wheelchair for the rest of their life. They end up with, mental issues where very similar to Alzheimer's. They can't remember things. They have damage to the brain. All these things can come from decompression sickness. I don't want that to happen to you guys, where you get arterial gas embolism, you end up with a stroke and potentially lose half your mobility or have mental issues, or even potentially die. Like, those are real type things that can happen. And the faster you ask for help on the boat, the faster I can give you emergency assistance, or the professional on the boats can give you assistance, and the more likely we're to get you in a chamber. Again, with Dan insurance, you're going to take care of all that cost potentially, and really potentially save your life and lifelong issues that you could encounter. Then last closing thoughts. Again, what I shared today is solely for informational purposes. It's not a substitute for training from a qualified instructor or agency. If you do want to know more, I highly recommend the book Deco for Divers by Mark Powell. I myself have a copy. It's an amazing book, both for technical divers and recreational divers. Always dive, though, within the limitations of your certifications. If you're not certified to go down past 120 feet or even 60 feet, don't do it, guys. It's not worth the risk. especially if you don't understand the limitations of decompression sickness and some of the things that can happen at depth that potentially put you at risk. And then if you learned something today, or if you're a technical diver, I asked you guys, share the information today, help other divers understand what's kind of going on, some of the recent studies that have come out around thermal exposure, or bubble versus gas content models, or any of these type studies, so that we can help others and make more informed, mindful decisions to help reduce their DCS risk. With that, guys, thank you for sticking through it. I know it's a long one. There's a lot to get through in this PowerPoint. Hopefully you guys like it. If you learned something, put it down in the comments below. Like, subscribe. Until next time, see you then.